Hello, this is Qiongxiu. Welcome to my presentation, PrivacyPreserving Distributed Graph Filtering. This is a joint work with Mario Coutino, Geert Leus, and Ms. Christensen. I will follow this agenda to introduce you this presentation. And now let's start with the motivation. So here is one example that to show the privacy issue in smart meters. So here is the power consumption data of our household. And you may think that it doesn't look quite sensitive information, right? It's not your fingerprint, it's not your bank account, it's not your facial images. But actually, it turns out by using this power consumption data, a lot of private information can be inferred. For example, whether you're away from holiday, or even your health condition, like whether you are disabled or not. So from here, we draw the conclusion that there's no real separation between your data and your identity. We should be really, really careful whenever we are asked to share our data. Now let's go to the problem setup. So we can model a network as a graph with a number of nodes and a number of edges. So here n is the number of nodes, m is the number of edges. This is one example. We have 5 nodes and 6 edges. The goal of distributed processing of our network is to compute a transformation over the network data x. And here we assume that this transformation is linear, so we denoted it as h here. And we summarize that there are 2 main requirements to be satisfied in this setting. So the first one is the output correctness. It means that, of course, each node want to gain its optimum result yi at the end of the algorithm. And in the meantime, they have the concern of privacy. So they would like to keep their private data secure from others. So here we define that this network data xi as the private data because it's the local information. And there are many ways to solve these problems, and existing approaches, they mainly use distributed signal processing tools, for example, distributed optimization. And there's very, very little exploration on graph signal processing tools. So in this paper, we would like to explore graph signal processing for privacy preservation. Now let's go to the proposed approach. And we need to first introduce the FIR graph filters. A popular way to implement, or we can say to approximate this edge, is to express it as a case order of polynomial of a matrix representation of this graph. And here we can write it in this way. And here S is the so-called graph shift operator. It characterizes this graph. It's an n by n matrix, and we can see that if these 2 nodes, node I and node J, are not connected in the graph, so we can see that the corresponding entry should be 0. So this graph shift operator characterizes graph. And the popular choice of this S can be, for example, adjacent matrix and graph Laplacian or their modifications. One good thing of this FIR graph filter is that it allows a very, very efficient distributed implementation. For example, we can see that here, the case shift of this network data, we can use its previous shifted version, and then we can multiply with S, and this S we can actually collect the data from your neighbors only. So it means that we can conduct all the computation locally with your neighbor only. So in this case, we can initialize this xi0 at the initialization. We initialize with your local private data xi, and then at each iteration we collect this from your neighbors, and then we sum it over. And then at the end we sum over all the case iteration, and then we get the final output. So overall, the implementation cost is very cheap. It's m times k, and it is very easy to see that the approximation accuracy is dependent on the filter order k. So if you want a higher accuracy, then you need a higher a bigger order K, but then the implementation cost is higher, right? So in order to address this issue, we have the so-called constrained edge variant FIR graph filter. And the main difference compared with the classic graph filter is that here the phi k is a scalar, but here phi k is an embedded matrix. So in this case, it allows more freedom to approximate this desired linear operator, such that a good approximation accuracy can be obtained by using a small order k. And in the meantime, the implementation cost is still m times k. Now let's talk about privacy. One important concept when talking about privacy is the adversary model. And it actually quantifies how robust is the algorithm when dealing with different kinds of security attacks. Here we consider two kinds of security attacks. And this is one toy example. Toy example here is eavesdropping adversary. It works by listening all the communication channels of the network to infer the private data. And here is the so-called passive adversary. It works by control a number of nodes in the network. For example, here node 1 and node 2 are passively corrupt. And what they do is that they try to collect all the information they have and send to this passive adversary and share with the passive adversary, such that this passive adversary will have all the information available to all the corrupt nodes. And then it will use this information to infer the private data of the rest so-called honest node. And one thing to notice here is that as long as there is one node corresponding to the edge is corrupt, then we can see that all the information transmitted along this edge is known by this corrupt node. So in that sense, we call this edge is corrupt edge. And having introduced this adversary model, let's see how does the traditional distributed graph filtering behave when dealing with these adversary models. So one thing to notice here is that since we are initialize xi0 with our private data xi, so we can see that this k equal to 0, right? So we can see that if this edge is being eavesdropped, then your private data will be known by the eavesdropping adversary. And for the case of passive adversary, if one of your neighbor is being corrupt, then we can see that this edge is corrupt, so that your information will be refilled. So it is very easy that the traditional distributed graph filtering refill the private data. So it is not privacy preserving. In order to address the privacy issue, the main idea is that since the problem comes from the fact that we directly share our private data to others. So in privacy preserving solutions, our main way to deal with it is that instead of directly share your private data, we first use some encryption function to encrypt our data first and then send out the encrypted data. And then we can call it as a noise insertion. So for example, we have the private data X and we have the noise R, and we can use this R to protect our private data X. We can add them together, or we can multiply them together. And in both ways, here is one example that how much information leakage would you have if you use these two ways to encrypt your data. And the conclusion is that as long as you increase the noise to signal variance ratio, it means that you insert more noise in here, then you will have a lower mutual information. And the mutual information is a metric to quantify how independent is these two random variables. So the more independent they are, so it means that the less privacy leakage it is. So overall, from here we can see that the more noise you add in the networks, then it means that you will get less privacy leakage. Having this in mind, now let's go to the detailed design of the proposed distributed graph filter. So in order to achieve the output correctness, we propose to have this encrypted network data and the encrypted linear operator, HE and XE. And in the meantime, in order to protect the individual privacy, we would like that each local private data XI and its encrypted version XIE to be to be sort of independent of each other. So the epsilon I is a threshold that determine how independent is these two random variables. So so one way to design this XE is that we can use what we introduced before. Here we try to use this encryption seed. We can try to choose this encryption seed EI to multiply with our private data, and then we get this encrypted data XIE. And overall, we can write it in a compact way like this. So we have this XIE, and then for the encrypted operator HE, we can actually write it in order to make sure that output correctness is complied. So we can see that HE we can write it in this way, such that the HE times XE is equal to the HX originally, right? And to solve this HE, in order to approximate this HE, we can use the introduced constraint edge variant graph filtering to try to find all the coefficient phi k to approximate this graph filter. And what we do is that we have an offline learning section that we rely on, or we can call it a centralized server or cloud that can conduct this offline learning to learn all the phi k, and then it send out all the corresponding phi k to each individual node. Now let's see how do we conduct it. So in this case, the initialization is conducted using the encrypted data, not the original private data, right? So we use the encrypted data to initialize the XI0, such that your privacy is being protected. And then when deal with the passive and eavesdropping adversary, the condition is actually very mild. So we rely that all the communication in the offline learning, for example, when you choose the encryption seed EI, you can choose this EI by yourself, and then you send out to the centralized server. So in this case, this communication should be securely encrypted, because if this encryption seed is being eavesdropped, then there's no privacy, right? But we only rely on this single iteration to be the offline step to be securely encrypted, but all the online implementation is okay to be eavesdropped, because all the XI0 doesn't come, is not private or sensitive information anymore. And in the meantime, since we rely on the centralized server to conduct all the offline learning, and then we assume that it should be trustworthy. So we assume that the centralized server is trustworthy, that he will not be corrupted, such that our privacy will be known by the adversaries. Yeah. So this is the condition that the proposed privacy-preserving distributed graph filter will be robust to both eavesdropping and passive adversary. All right, now let's go to the numerical result. Here the first result we conduct, the first experiment we conduct is we try to show the approximation error between the proposed constrained edge variant graph filter and the known private preserving. It means that the traditional constrained edge variant graph filter for different using different filter order k, and then the top result is the result for the exponential kernel, and the bottom is for the ideal low pass filter. So we can see that in both cases, we either the price to pay for achieving privacy preservation is that we either need to sacrifice a bit the approximation accuracy, or we need a little bit higher order to achieve the same approximation accuracy. So there's a price to pay to achieve privacy preservation. And another question you might ask is how does it compare with the existing distributed optimization approach? Here we compare with a proposed approach using PDMM. And we can see here is that for the distributed average consensus problem, we can see that the proposed graph filtering actually require very low low iteration number to achieve a fairly good approximation error. So that it is, so this is the main advantage of graph filtering compared with distributed optimization. It requires less iterations, so it's more communication efficient. But the one shortcoming is that it will saturate at certain error floor, but the PDMM, the distributed optimization approach can still converge if you allow more iteration. Yeah. And overall, we can compare them here is that the proposed approach and the distributed optimization-based approach, they all consider the same security model. They are both information theoretic. They use noise insertion to protect the private data, and they consider the same passive and eavesdropping adversary model. And the difference is that the proposed approach has the accuracy is approximated, is not accurate. And the communication complexity is m times k, but for the optimization is m times t. T is the overall iteration number, which is really very big, and they both require a certain amount of secure encryption channel to make sure that the encryption seed is not being listened or eavesdropped by the eavesdropped adversary. And one difference is that the proposed approach, it doesn't require any honest neighbor to protect the private data, but the distributed optimization require at least one honest neighbor. And another thing, the last thing is that the proposed approach rely on the trusted third party, which is the centralized server, to conduct all the offline setting, but the PDMM is fully distributed, it doesn't require any centralized server. Now let's go to the conclusion. So here in this paper, we propose a privacy-preserving distributed graph filtering algorithm. And the main advantage is that it is communication computationally lightweight, and is a competitive alternative with the distributed optimization-based approach. And one shortcoming of this approach is that it has a trade-off between privacy and the approximation accuracy. That's all. Thank you.